Hello, my name is Scott Streckenbach, and I'm a member of the MGH Cardiac Anesthesia Group. I'm also the Director of Perioperative Electrophysiology at the MGH, and I want to welcome each of you to my course on the perioperative management of pacemakers. This course was developed to help cardiac anesthesia fellows, staff, and eventually even residents to learn the fundamentals of pacemakers. And I'm hoping that this course, along with your hard work, will help each of you learn enough to be able to manage almost any patient's pacemaker in the perioperative setting independently. Now, learning about pacemakers is a long and hard road, and some of the topics will be more difficult than others to comprehend. Certainly challenging corners will arise, but I'm hoping that with repetitious learning techniques, I think that all of you will be able to make it to the end of the road successfully. It's my hope that you're developing a core understanding of these devices will give you a critical platform from which you can continue learning about each pacemaker encountered in the clinical setting. And I hope that you will then be comfortable using the assistance of our EP physicians, the company reps, industry tech support, and even my support to continue learning about pacemakers as you continue your practice in perioperative electrophysiology, much as I have done in the past 7 or 8 years. All right, so let's start with lecture 1, and we're going to talk about basic components of the pacemaker, pulse generator, and the leads, and then we're going to also talk about some physiology specifically related to electricity, pacemaker batteries, and the action potential. Now, pacemaker anatomy, if you think about it, it's pretty simple. You have the pulse generator, which is usually in the left subpectoral position, sometimes on the right, sometimes in the abdomen, but typically here. And then connected to the pulse generator would be anywhere from 1 to 3 pacemaker leads, and one typically ends in the atrium, and another typically ends in the right ventricle. The third, oftentimes now, for patients who have problems with conduction, bundle branch blocks, and heart failure, the third one would typically be in the coronary sinus. Now, if you take a closer look at the pulse generator, there is a case that surrounds the important components within. This case is hermetically sealed. That basically means that there's a hermit living inside. In other words, this is all independent, completely sealed from the outside, or at least we hope it's completely sealed from the outside. There is a battery that supports the circuitry or the command center, and then the command center is connected to the port where the pacemaker leads are inserted. And so that's how there's communication to the leads. Now, if you look closely at this, the circuitry, there is a command center here, the logic center, the timing control center, all kinds of clocks and all kinds of decision branch points and so on. And basically this command center has to get information from the electrode that's on the heart, and it senses any intrinsic activity in the heart. That information is put into this control center, and then the control center makes a decision whether or not it's going to send a pacing impulse back out to the myocardium. So that's really the sort of the key system that the pacemaker circuit works with. Now, there's also a part of the circuit that is memory, and that allows the programmer to look back and see what happened in particular events in the past week, month, year. There's a telemetry circuit, which allows the programmer, you or I, to use our programmer to manipulate how the pacemaker is going to work in the future, so we can turn off the rate response mode, for example. Speaking of rate response modes, the physiologic sensor that is typically associated with just about every pacemaker nowadays is also connected to this programming circuit, and that might be a rate response mode, it might be a minute ventilation mechanism, and then finally there's a battery power management system that's connected in here as well. This is a picture of an actual pacemaker. This is the battery, the bulk of the pacemaker. Here's the circuitry, and you can see how the circuitry is connected to what's called the header, where the pacing leads are connected. Now, the pacemaker leads have basically two important functions. One is to sense the intrinsic myocardial electrical activity, to tell the pacemaker what the heart's actually doing on its own. And then the other function of the lead is to deliver the electric pulses to the myocardium when a pacing spike or a pacing pulse is indicated. Now, the pacing leads can be either endocardial, that's the typical scenario, but sometimes they are placed epicardially. And when you think of a pacemaker lead, you want to think of the 6 components. There's a connector pin or pins. There's insulation, the conductor, which transmits the electric pulse from the battery down to the myocardium. And then there are typically two electrodes, a ring electrode, which is proximal, and then a tip electrode at the end. And then there's some type of fixation mechanism to make sure that the pacing lead stays where it's supposed to. Now, if you look, let's look at these 6 components a little bit more closely. The connector pins, the older versions had 2 separate pins for each electrode, but now most of them have one single connector pin that goes into the connector port, or what's called the header. And the important thing to remember here is that all current bipolar pacing leads are compatible with all current manufacturer header designs. So if you look at a patient's medical record, you might see a St. Jude pulse generator and Medtronic leads. And that may just be because the patient had a Medtronic pulse generator and Medtronic leads 6 years ago. And the battery of that Medtronic device was low. They replaced it with a pacemaker that may have been more specifically designed for that patient, that may be a St. Jude device. And the concept here that I want you to take home is you want to look at, when you look at someone's record, look and make sure you determine what the manufacturer of the pulse generator is, not necessarily the leads. And that's because you have to use a specific programmer for that pulse generator. So if you have a patient with a St. Jude pulse generator and Medtronic leads, you have to use a St. Jude programmer, not a Medtronic programmer. Okay, and we'll obviously talk about this more in the programming section. Now, the connector pins should extend beyond what's called the distal set screw in the header block, and this is just sort of an intro to when we get into troubleshooting pacemakers. And if the screw is not all the way in, and this is not an uncommon mechanism of pacemaker dysfunction, if it's not all the way in, then you'll have sensing artifact or failure to pace. And I'll zoom in on this picture so you can get this concept. So if you look at a chest X-ray, you want to make sure that the connector pin is past this distal set screw. So this is a bad situation, and this is a good situation. Okay? Now, the conductors, the major concept behind conductors is that they all transfer electrons well. So the battery creates the electrons, and then the electrons have to get out to the myocardium, and the way they do that is to travel through different types of metals, whether it's cobalt, nickel, chromium, molybdenum, silver, platinum, etc. These conductors bring the electrons to the myocardium. Now, these leads, and therefore these conductors, move around a lot, and there are about 40 million heartbeats a year. And you want these electrodes, these leads, and therefore these conductors, to be very resilient and flexible. And so they are typically multi-filar, and they're also coiled to increase the reliability and the flexibility. And if you look here, this is a typical lead, and you can see how it's coiled. If you took a zoom in on the cross section here, you'd see that the lead is multi-filar. And if you look here, you see, so this is the conductor for the distal electrode. This is the conductor for the proximal electrode. And then you have insulation separating the two conductors, and then also separating the conductors from the body. And this insulation is very important, as the conductor is, because the insulation keeps the electrons from going into the body. And there are two types of insulation, and that is going into the body where you don't want it to be going. You want it to go into the myocardium, not into the chest wall, for example. So there are two types of insulation. There's polyurethane, which is thinner and also more slippery than silicone. And then the silicone is thicker, larger, and less slippery. However, silicone is more durable. So there's sort of a trade-off between the two different types of insulation. The bottom line is the insulation needs to be intact. If it becomes disrupted, then there will be lead dysfunction. Now, as you move from the connector pins down along the conductor and the insulation, eventually you're going to get to the electrodes. And again, there are typically two electrodes. Now, we'll talk about this in a minute, but there are either bipolar electrodes or unipolar electrodes. And what the difference is the number of electrodes that are actually in the heart. And this, most of the time, it's a bipolar electrode like this, and you'll have a distal or tip electrode here, which is typically a smaller surface area electrode, and then you'll have what's called the ring electrode, or the more proximal electrode here. And one conductor goes from the battery, goes through this ring electrode. It's electrically isolated from that electrode and goes all the way out to the tip. And then the second conductor is connected to the ring or proximal electrode. Now, when the lead is put in, the electrophysiologist tries to put it in a specific location. He or she will test the amount of energy required to pace in that particular position. He or she will measure the amplitude of the P wave or the R wave in that particular position. And when the lead looks like it's in a good place, the cardiologist is going to want us to stay there. And so there are different types of fixation mechanisms. One type is called the passive fixation, and the passive fixation leads have tines that become entrapped in the trabeculae, and therefore there are limited sites for insertion, so that you couldn't really put this kind of a lead out in the RVOT where there really aren't any trabeculae. The good thing about the passive lead is that it's unlikely to perforate. It probably doesn't get secured as fast as an active fixation lead, but once it is secured, it's pretty difficult to remove. The active fixation leads are what also known as screw-in electrodes. And you can see here that there is a corkscrew-like electrode here that actually goes right into the heart. Now, obviously, if that is screwed in too far, it can perforate the heart, and so that's one of the downsides of the active electrode. But the upside is that it's secure more quickly than the passive fixation lead, and it allows you to put it into just about any place in the atrium or the ventricle because you can put it in the RVOT, for example, where there are no trabeculae. It is also easier to remove, and there's less fibrosis around it because you don't have these tines, and it's essentially isodiametric. So if you're trying to remove it, and we do this all the time now, we take out leads that are either infected or not working. With a process called laser lead extraction, this is a little harder to take out than this one. And you know, the take-home message for you here is when you're planning to do a lead extraction, it's useful for you to find out, number one, if it's an ICD lead or a pacemaker lead, because ICD leads are bigger, then they're going to be harder to remove. And then you also want to find out if the leads are active or passive fixation leads, because that'll also give you an idea of the likelihood of problems when the lead's being removed. This is just a more detailed picture of the active fixation lead. So that you have, and when the lead's going in, the corkscrew device, so the corkscrew electrode is inside the lead. When it's in position, then a stylet is used to rotate that electrode into the myocardium. Now, I mentioned earlier that most of our leads that we deal with are endocardial, but certainly not all of them. For example, a patient who has a mechanical tricuspid valve obviously cannot get an endocardial lead in the right ventricle, or in some patients you just can't get good capture thresholds and so on. So every once in a while the surgeons will put epicardial leads on, and this is just an example of a ventricular epicardial lead and an atrial epicardial lead. And we'll see these in the chest X-ray section. Now, if you look in sort of a pictorial image of what it would look like in the heart, here you can see an active fixation lead and a passive fixation lead. The other type of a lead that doesn't really have a technical term in terms of its fixation mechanism, but if you want to think about it this way, these leads are fixated geometrically. In other words, they are shaped in a way that favors their retention in the coronary sinus after being placed either in the coronary sinus itself or one of the branch veins of the coronary sinus. These leads are certainly more susceptible to being dislodged, particularly during cardiac surgery when cannulae are pushed into the right atrium. They can also be dislodged if you're struggling with PA line insertion. And so certainly you want to make note of whether a patient has a coronary sinus lead or not in the preoperative assessment of your patient. By the way, this configuration, if you look at these leads, this will, knowing what these look like, in addition to knowing that they're in the posterior aspect of the heart, because that's where the coronary sinus is, will help you discern by chest x-ray what type of a lead or leads the patient has. And just to summarize the sort of lead discussion here, here's the connector pin. This is a typical coaxial bipolar electrode. Here's your conductor, the insulation around the conductor. Actually, here are your two conductors, one inside the other. One conductor ends at the proximal electrode and the other at the distal electrode, and then this is the fixation mechanism, in this case a passive fixation mechanism. The clinical concepts that I think are useful to take home with you, the active fixation leads are more readily secure than passive ones. Passive fixation leads are typically harder to extract. Coronary sinus leads used for cardiac resynchronization therapy are most susceptible to dislodgement. And if you're going to place a PA line within a month of a new lead implant, certainly consider fluoroscopic guidance, or at the least, make sure that you have a backup pacing mechanism available, and also that you check the lead integrity, impedances, and capture thresholds immediately post-op, or certainly before the patient leaves a monitored setting. So that's sort of our brief discussion of pacemaker anatomy. And now we will talk a little bit about pacemaker physiology, and we'll talk about the basic electrical circuit, some terminology, electrical terminology, pacemaker batteries, and then finally action potentials. Now, if you think of a simplified pacemaker circuit, free electrons are created in the pacemaker battery's anode, and then these electrons flow through an insulated lead, through a conductor, to the lead's distal electrode, and then those electrons escape into the myocardium, hopefully capturing the myocardium, and then the free electrons flow back into the lead's proximal electrode and back to the battery's cathode, completing the circuit. And that's just the general concept of electricity. Now, here's a pictorial diagram of that, and these blue dots all represent a bunch of free electrons that have been created in the battery, in the battery's anode, and then current, or there's some conductor that's open now going through the myocardium. This is sort of your load, and those electrons are flowing through the load and then back into the conductor, all the way back into the red sort of binding sites or homes for all of these electrons. So the electrons really want to go from here to their vacation spot over here. And as long as there's an intact method for them to do that, then the current will flow. If there's a disruption here, however, the current will not flow. And I just want to go over very basic terminology, and certainly this isn't something that you want to spend a ton of time remembering, but just hopefully just the recognition of these terms will be enough. A coulomb is a unit of charge, and it represents the charge of approximately a lot of electrons. I'm not going to even try to mention this number because some of you will try to memorize it. It's a coulomb is a bunch of electrons, a quantum of electrons that we use when we talk about current. The volt is a unit of electric pressure or electromotive force that causes current to flow. And if you think about it in the terms of a battery, if you think of that diagram we just looked at, you have a bunch of free electrons on one side that want to move to the other side. So you have this built-up tension or this force or this voltage that is quantifiable, and that's kind of the concept behind the volt. And a similar way to think about this is if you hold a 10-pound weight in the air above, say, a light bulb, and as you hold it there, there's this built-up tension created by the mass and the acceleration of gravity, so you have this force. Well, the same kind of concept is true for voltage when you have a bunch of electrons waiting to fall or to go to the other side of the battery. So a volt is therefore a measure of electric potential that refers to the energy that could be released if electric current is allowed to flow. Electric current, and we oftentimes use the abbreviation I for current, is the movement of electric charge, usually through a wire, measured in coulombs per second. So how many coulombs pass by this point per second is a measure of the electric current. And of course, the ampere is the measurement unit we use for electric current. It represents a charge moving at the rate of 1 coulomb per second. And most of you recognize that when we talk about pacemakers, we're talking about much smaller amounts of current. And so instead of using the ampere, we typically use the milliampere. Resistance, R, is the simplified measure of the opposition to flow of electric current. And we will typically talk about impedance, which is a combination of several types of resistance that the pacemaker circuit includes, and that includes the resistance across the lead conductor itself. But there's also resistance to current flow or electron flow from the lead electrode to the myocardium and from the myocardium back to the other part of the lead. And then there's also something called polarization resistance, and I don't want to get into this in too much detail, but as electrons are being fired out to the myocardium, there can be a buildup of electric charge or negative charge at the myocardial electrode interface, and that can also lead to some resistance. So resistance is not simply static, it's also dynamic. And resistance, not surprisingly, is measured in ohms. The ohm, or 1 ohm, is the resistance that results in a current of 1 ampere when a potential of 1 volt is placed across the resistance. And we're going to talk a lot about ohms because we're going to measure the impedance not only of the leads but also of the battery. And in general, a pacemaker lead will have an impedance somewhere between 300 to 800 ohms, and ICD leads by contrast have impedances in the 50 to 60 range. But the bottom line is when we interrogate our pacemakers, we're going to look at the impedance of the leads, and we're hoping to see a pretty consistent pattern over time. When there's a significant increase or decrease in the impedance of a lead, we will then know that there is something wrong with the lead, whether it's an insulation issue or a conductor issue or a connector pin issue. Hard to know for sure, but there's usually a way to figure that out. But we will be looking and talking impedance a lot. Ohm's law, most of you have heard of this. Voltage equals current times resistance. We'll also think of it as current equals voltage divided by resistance. And if you think of the voltage as a pretty constant number, and that is the battery's ability to generate the free electrons. If you have, again, a pretty stable voltage and your resistance goes up, then the current is going to be low. If you have low resistance, then the current will be high. The joule, we'll talk a little bit about this in our discussion about pacemakers, and the joule is a unit of work or energy, and it's equal to the energy transferred when passing a current of 1 ampere through a resistance of 1 ohm, and the key is it has an element of time for 1 second. So it's voltage times current times time, and because a pacer pulse has an amplitude and a duration, it therefore delivers microjoules of energy with each pacing pulse. So the electricity summary can be summed up with this little diagram. Voltage equals current times resistance. The voltage is the force or push that causes electrons to move through a circuit and is provided by the pacemaker battery. The current is determined by the amount of electrons that move through a circuit and causes the myocardial cells to depolarize, and then impedance is the opposition to the flow of that current. Now, if you look at a battery, a typical lithium iodine pacemaker battery, the anode over here is the side where electrons are created. So the two lithium atoms are converted to lithium ions plus two free electrons. And those electrons want to escape and move over this way, and so the electrons flow over to where the reduction process is going on in the battery's cathode, where iodine plus two electrons are used to create two iodide ions, and the iodide and the lithium ions then combine in an equation to develop lithium iodine, and that is a solid that over time builds up and it increases the resistance in the battery, and we will use that increased resistance to help us measure the remaining battery life. And it's really, I want you to notice that the electrons in this circuit are moving from the anode over to the cathode. And one way to talk about current is to talk about which direction the electrons are moving. Now, there's also a way to talk about current, and that's the conventional, or the old, as actually it says conventional, but it's the way that they used to talk about current flow, and that is in the opposite direction. So if you just talk about current flow, people will talk about it going from the cathode back to the anode, but I will try, for the most part, to talk about the flow of electrons. It just seems to make more sense to me. So the electrons go from where they're made to where they're used. Okay, and we'll talk about this concept a couple times during the next few lectures, and I just want to introduce it to you here. Now, when you talk about the battery life in a pacemaker, the lithium iodide that forms during the battery use is a solid, as we talked about, that gradually increases the separation between the lithium and the iodine in the battery. And this separation slowly increases the battery's internal resistance. So the battery does not run down due to depletion of chemicals, but rather it runs down because the internal resistance of the battery increases, which causes the voltage to drop. And so when we assess a pacemaker's battery life, we're going to measure the internal resistance of the battery, which will reflect its remaining life expectancy. And one can graph these concepts, the voltage here in red on the left, and the internal resistance in blue on the right versus time. And when the battery's brand new, there's about 2.8 volts, and that 2.8 volts lasts for up to 90 months. And then all of a sudden, and this is ballpark, it could be 7 years, it could be 12 years, it just depends on the amount of battery use, how many times the patient's pacing and so on, but the bottom, you get the concept is that over time, there becomes a point where the battery voltage falls relatively quickly, and simultaneous with that, there is an increase in the battery's internal resistance. And the internal resistance is relatively easy to measure with the programmer, and so that's what we typically will do. And you can see if you place on here sort of terms that you'll use. BOL you'll see on a programmer sheet, and that refers to the beginning of the battery's life. ERT is the elective replacement time, and that happens sort of at about a 2.5 volt or 5 kilo ohm internal resistance. And then eventually the battery's voltage and resistance will get to the point where the signal is the end of life. And these time periods are typically reflected not only when you use your programmer, but they can also be reflected in the response the pacemaker will have to the to the magnet. So the pacing rate associated with the magnet changes at the ERT and at the EOL. So the next thing we'll talk about is the action potential generation. And if the electric current delivered by the battery and the lead is sufficient to activate the viable and resting myocardium contiguous with the lead's electrode, an action potential is generated and the heart depolarizes. And so we need to know a little bit about the action potential. I don't want to go into too much detail, but this probably is familiar to most of you. And if you think about phase 0, you think of a rapid inward sodium current, and a rapid inward sodium current that depolarizes the cell from minus 70 millivolts up to positive 15 millivolts in this case. Phase 0 is a rapid outward potassium current, but then very quickly in the myocytes there is an inward sodium and an inward calcium current that sort of compensate for the outward potassium current, and the cell has what's called the plateau phase, phase 2. And then eventually when the inward sodium and inward calcium currents stop, the outward current continues, and that leads to phase 3 of the action potential, and then eventually it gets back down to minus 90 millivolts, and then you have phase 4. Now, phase 2 of the action potential is essentially the absolute refractory period of the myocyte. There just aren't enough sodium channels that can be opened to regenerate an action potential. So that's the absolute refractory period of the myocyte. Phase 3 is essentially the relative refractory period of the myocyte, and the further you get down here, the more likely stimulus is to recreate another action potential. So if you try to recreate the action potential up here, it would take a pretty high stimulus. Down here, a slightly supranormal stimulus, and once it gets down to the phase 4, then the myocyte's ready to go again, and any kind of pacing stimulus would pretty easily depolarize that myocyte and regenerate an action potential. Now, if you look at the action potential superimposed on an EKG, then you will see that the beginning of the action potential represents the very beginning of the QRS complex, and here it's a Q wave, and then the remaining component of the QRS and the ST segment sort of represents the absolute refractory period of that myocyte. And then the T wave, in this picture, it sort of says that the relative refractory period is the ascending limb of this T wave, and it probably varies a little bit depending on the myocyte and the milieu that myocyte's in, but somewhere in the T wave, in the proximal and maybe the mid section of the T wave, the cell is in its relative refractory period. And then once you get to the descending limb of the T wave and anywhere out here, you're in the normal myocardial status. So the pacing impulse, no problem to deliver, no problem depolarizing the myocyte here. Okay? Now, it's really important to recognize that if you have a pacer spike, if you see a pacer spike here, or here, or here, superimposed on your EKG, you should not expect that pacemaker spike will cause another depolarization, because it's in the myocytes, that myocardial segment, the absolute refractory period. So you don't have to worry about a pacer spike here. You might say, oh man, I'm going to cause VF. No, you're not here, okay? So pacer spikes here, number one, they aren't going to pace the heart, and number two, they're not going to cause VF. It's the pacer spikes that fire over here that have the possibility, and it's not a likely possibility, but there is a possibility that you could stimulate the heart and cause VF, okay? So pacer spikes here will not pace the heart. They shouldn't pace the heart. If you see a pacer spike here and it's not capturing the heart, that doesn't mean that pacemaker is malfunctioning necessarily. Okay, we're going to talk a lot about this in future lectures. So what are the take-home points from lecture number 1? Well, the overall goal of this program is to help each of you develop the ability to manage pacemakers in the perioperative period on your own. A pacemaker consists of the pulse generator and 1 to 3 leads. The leads can be fixated passively, actively, or geometrically with respect to the coronary sinus, and the coronary sinus leads are the most susceptible to being dislodged, particularly during cardiac surgery. Leads less than 1 month old are most susceptible to displacement during PA line insertion or cardiac surgery. If the lead battery connection is lost, or if the conductor is fractured, or if the insulation is compromised, or if the electrode is dislodged from the heart, the current will not flow to the myocardium and the pacemaker will not work. And that's sort of the framework you want to think about whenever you have a pacemaker problem, is you want to think systematically of what things could go wrong to prevent the pacemaker from working. Now, even if the pacemaker is working perfectly, if the myocardium is suboptimal,
A fully functional pacemaker may not pace the heart. Then voltage is equal to current times resistance, or current is equal to voltage divided by resistance. The electric pressure is measured in volts, current in amps, resistance in ohms. As a pacemaker battery depletes, remember that its internal resistance increases. A pacing stimulus cannot capture myocardial cells that are in the absolute refractory period, or basically the plateau phase or phase 2, or the QRS-ST segment. Okay? A pacing stimulus can capture myocardium in the relative refractory period, or phase 3, or the T wave if the stimulus is strong enough. So this ends the first lecture, and this is a quote that I think is very interesting. It's, "Quality is never an accident. It's always the result of high intention, sincere effort, intelligent direction, and skillful execution. It represents the wise choice of many alternatives." And I think that this is the approach that we're going to take with learning how to use the programmers and to learn about pacemakers in general. Thank you for your attention.